Last week, actually, we just defined what is the meaning of density, right? This symbol is rho. So from the density, you're able to find out the mass. This density, not only density of object, it can be a density for any substance. Density of air or gas, density of liquid or density of solid can be also used the same definition. So pressure as well. So pressure is defined as force per unit area. So the SI unit for pressure is Pascal or Newton per meter square. The other units for pressure is ATM or atmosphere or torr. Torr is similar to millimeter mercury. So just for information, for atmospheric pressure at sea level is 1 atm, which is about 1.01 times 10 power 5 Pascal, or approximately equal to 101 kilopascal. That is the atmospheric pressure at sea level. So it's also equal to 760 torr, or 760 millimeter mercury, or 14.7 psi. PSI stands for pound per square inch. So look at this diagram. So let's say this is the Earth's surface or at sea level. As the height increase, pressure decrease with altitude. Okay, it is due to the density at the higher location or near to space. The density here is almost zero, and therefore the pressure is zero. Okay, but the location near the surface of the Earth, the air density here is high, and pressure here is high as well. Pressure in fluid basically is increased with depth, where the pressure in fluid is equal to P naught plus rho GH. So this rho here is the density of fluid, and the H will be the depth of fluid. For example, this is the lake, and here is the water of the lake. Okay, let's say I have 2 points, point A and point B. So as long as point A and point B at a location with the same depth from the surface of the water, that means same H. This is a H, and therefore the pressure at point A is same as pressure at point B. Pressure in a fluid is equal to atmospheric pressure plus rho GH. Atmospheric pressure means the pressure at sea level. So this is a level surface. So here is, at this point, has the atmospheric pressure of P naught. So the total pressure inside the fluid is P naught plus rho GH. Okay, so pressure at point A is P naught plus rho GH. So same as pressure at point B is also P naught plus rho GH. At static equilibrium, pressure at point A is equal to pressure at point B if they have the same depth. The condition is it is only valid at static equilibrium, right? All the points at the same depth are at the same pressure. Okay, so you can see that point A, point B, point C, and point D, all right, they are at static equilibrium, right, not moving. So as long as it's the same depth, same height, vertical height, so no matter what is the shape, at point A, point B, point C, and point D, the pressure at each point is actually the same. Pressure in fluid increase with that. Okay, for example, this is water, so at the bottom here has the highest pressure. So it is actually similar to a block, for example. So the bottom block here needs to support all the blocks above. Pressure is equal to force per unit area. If you're referring back to the same cross-section area, bottom, the force will be the highest, and therefore the pressure will be the highest. So same as the layer in a water level, so the layer at the bottom have to support all the fluid above on it. So that's why the pressure here will be the highest. So now let's move on to this barometer. Mercury barometer. Okay, mercury barometer means the fluid used in the barometer is mercury. We have water barometer or any other, use any other liquid. Barometer basically is a scientific instrument used to measure the air pressure at different environment or different location. Atmospheric pressure is 1 atm. It is also equal to 760 millimeter mercury. So if you're referring to this mercury barometer, this barometer is placed in the atmospheric pressure. So the H of the mercury is always equal to 760 millimeter. Okay, that's how you get the 760 millimeter mercury. Okay, point B is exposed to atmospheric pressure. So point B has the atmospheric pressure of P atm. So inside the barometer, on top here, it must be vacuum. Pressure here is 0. So the pressure at point A is rho GH. So we are using rho as the density of mercury. So 13600. G is 9.80. Multiply with H. If the barometer is placed at the environment of atmospheric pressure, so the H here is always 760 millimeter, 0.76 meter. Okay, round it off to 101 kilopascal. So that is how you get the atmospheric pressure in unit Pascal. Okay, so the first principle that I'd like to introduce to you is called it as Pascal principle. According to Pascal principle, the pressure applied to any part of the enclosed fluid can be transmitted to every point of the fluid and also to the wall of the container. Firstly, you have to refer to one enclosed fluid. Okay, so for example, I have enclosed fluid in a container. So here there is a piston. Okay, and I call this as piston 1 with the cross-section area of A1. Another piston, there's another side. Okay, maybe this is another piston with a cross-section area of A2. In this container is filled with fluid. So this one we call it as enclosed fluid. Okay, so the pressure exerted on one point, point 1 on the left arm of the container, the pressure exerted on this point can be transmitted to every point inside the fluid, including the wall of the container. Of course, the piston. The pressure can be transmitted. So which means if I know what is the pressure exerted on point 1, P1, the pressure exerted on point 2 is actually say P1 is equal to P2 because the pressure can be transmitted to every point within the fluid. The condition is it must be in the enclosed fluid. The force that exerted on point 1, F1, pressure exerted on piston 1. So this pressure can be transmitted to piston number 2. Okay, same as P2 is equal to F2 over A2. Okay, how can it transmit? So of course, it can transmit it through the fluid, so the direction will be opposite. So you will actually exert it on this, which is the F2. So if you know the force exerted here, and then therefore it may actually lift up the piston because as you push it down, right, on piston number 1, so piston number 2 will be trying to push up within this enclosed fluid. So this is what we call it as Pascal principle. So how do we apply it? So you can use the equation of P1 is equal to P2, so P1 is F1 over A1 is equal to F2 over A2. So pressure on piston 1 is F1 over A1, pressure on piston 2 is F2 over A2. Ratio of F over A is a constant. So from here you can also conclude that F is proportional to the area. I mean, if you increase the area, so the force exerted on this area will be increased as well. Okay, so as I shown in this diagram, piston 1, the area is smaller, so you may just apply a smaller force on piston 1. The force exerted on piston 2 is higher because area of piston 2 is higher. Okay, why is it? Because F over A is a constant, which implies that F is proportional to A. Higher area, the force exerted on the piston will be higher as well. We use it in a hydraulic brake system. You just need to apply a small force on a smaller area, but you are able to lift up a large object. This is the application of Pascal principle. Okay, now we further investigate the Pascal principle. Okay, so if you apply the force F1 on piston 1, which has an area of A1, so you should expect that this piston will be moved down by the distance of D1, for example. So for piston 2, it will actually lift up to this level, for example, and here is with the distance of D2. This fluid is within the enclosed fluid, all right, and therefore the volume of the fluid in this part is same as the volume of the fluid in this part. So how to get the volume? V1 is equal to V2. V1 means this part. V2 means here. So how you get the V? V means A cross-section area multiplied with the displacement. V2 will be A2 multiplied with the displacement of D2. D1 over D2 is equal to A2 over A1. And from Pascal principle, F1 over A1 is equal to F2 over A2. So I rearrange the Pascal principle to make it a ratio of A2 to A1. So A2 to A1, A2 to A1 is equal to F2 to F1, right? So happen A2 to A1 is equal to D1 over D2. So I substitute inside here. And eventually you will get D1 over D2 is equal to F2 over F1, or F1 D1 is equal to F2 D2. So you have to remember this relation. So basically the product of force and displacement, this is actually work. Right? This work we call it as input work because we applied the force of F1 to piston 1. 1 is piston number 1. And F2 D2 we call it as output work. So when input work is equal to output work means the efficiency is 100%. So which means this is the ideal case. There is no friction at all. So you have to remember this field relation. Yeah. So the first one is Pascal principle. The pressure can be transmitted to every point within the fluid. The second relation is F1 D1 is always equal to F2 D2. Okay, input work is always equal to output work for an ideal case. Okay, so now we proceed to the next one, next principle, call it as Archimedes principle. So any object is either completely or partially submerged in a fluid, is buoyant up by a force where the magnitude is equal to the weight of the fluid displaced, or in short, buoyant force, Fb is equal to the weight of the fluid displaced. So just imagine that you have a container. Right, so initially it's filled with fluid and it's full. Okay, and when you add the object into this container, so let's say this is the object, so the extra fluid displaced from the container, okay, and the weight of the fluid displaced, is equal to buoyant force. That is the statement of Archimedes' principle. Archimedes' principle. Buoyant force is equal to the weight of the fluid displaced. So this buoyant force is actually the upward force exerted on the object, right? So this object is called as completely submerged. So for partially submerged, the object will be something like this. We have the same container, filled it with fluid. So if the object, it may be partially submerged only. So you still have one force, upward force to acting on the object, so that the object will be partially submerged. So this upward force is called it as buoyant force. So according to the Archimedes principle, right? According to this principle, the magnitude of the buoyant force is equal to the weight of the fluid displaced. So what is the meaning of weight? Weight means mg. Right? So m of the fluid displaced multiplied with g. Okay, so usually we'll know that what is the density of the fluid. Density is defined as mass per unit volume. Therefore, mass of the fluid is equal to rho of the fluid multiplied with volume of the fluid. So mass is equal to rho of the fluid multiplied with the volume of the fluid displaced multiplied with g. The buoyant force is equal to rho vg. So this condition, we call it as totally submerged condition. This one is called it as partially submerged. Can be totally submerged, or sometimes we also call it as completely submerged. For a completely submerged object, volume of the fluid displaced is actually equal to the volume of the object. For completely submerged, FB is equal to rho of the fluid displaced multiplied with the volume of the object multiplied with G. This one is only true for totally submerged or completely submerged object, right? So what happened to the partially submerged object? So for partially submerged object, in this case, the buoyant force is actually, the magnitude of buoyant force is still equal to the rho of the fluid displaced multiplied with volume of submerged portion multiplied with G. Volume of the submerged portion means this one. Buoyant force magnitude can be also found out by comparing the actual weight and also the apparent weight. Right? Actual weight means the weight that you measure when you place the balance scale in air. Apparent weight means the reading that you get from the scale when you place the object in a fluid. You place the weighing scale in air, this one you call it as actual weight, right? So the reading you get it when you place the object in a fluid, this one we call it as apparent weight. So of course, there is a buoyant force acting on this object. The reading in the apparent weight is less if you compare with actual weight, right? And the difference between the actual weight and the apparent weight is actually equal to the magnitude of buoyant force.